much of the story from the last few contributors. And I'm also very pleased to realise that what we did result in some useful end products, finally. Despite the views that we expressed about the success or lack of success that NRDC had in its supporting business. Now, the corporation wasn't created specifically to deal with computer industry development. It was, in fact, created as the end product of quite a long period of policy debate that had gone on, or even consideration of the problems which led to it were around before the First World War. And as a result of the First World War, there was a lot of discussion about what should be done to try and stem what was perceived as the decline of industry, science in the UK. But nothing came of this, although various solutions have been suggested on both sides. But the subject came to the surface again early in the Second War, in the last war, when rather far-sighted people like Blackett saw there was a need to do something to ensure that results which would be coming out from government-supported research, primary defence purposes, could ultimately be used for the benefit of UK industry. And this debate went backwards and forwards, Board of Trade, the Treasury, and other departments all arguing about it, had their own views on what should be done. Until, I suppose, about 42 or 43, some solid ideas started to come to the surface. And by the end of the war, this had taken shape, and under the aegis of Wilson and Stafford Cripps, the development of inventions bill was put together and debated, and this resulted in the passing of the Development of Inventions Act in 1949. No, the act was in 48. In 48. But it's important, I think, to realise that the ideas that were around for the corporation at that time were based essentially on the primacy of patented inventions. It's all to do with having patents and exploiting them. The rather simplistic view was that if you had patents, you could get industry to take licenses, they would use them, and the process would go on naturally. They would produce products and sell them, and this is all good for it. Now, the discussions were also complicated by the fact that people concerned were primarily concerned with the inventions, results of research that would be going on in publicly supported places, in the research establishments and universities. And the principle applied that work done under publicly supported contracts would result in the industrial property rights belonging to the Crown, so that the government departments who started it off would then have the task of trying to do something about it. So that emphasized again the concentration on handling patents. It also constrained in whatever they did, because there was a general principle of fairness that had to be applied. Contractors couldn't be given any unfair advantage, so that rights couldn't be left with them or they couldn't be chosen specifically. Things had to go through open tendering process. Now, the Act, when it finally was passed, set up a non-government independent executive body, so that it wasn't a civil service organisation, although it owed allegiance to the Board of Trade. And in order to perform its functions, which I'll come to in a moment, it had powers to borrow up to £5 million from the Board of Trade, and it was required, in exercising its functions properly, to repay this money, I think, within 5 years, with interest. Now, it sounds a nonsense now, but it never was repaid. Subsequently, there were later amending acts which increased the ceiling of borrowing, extended the repayment period, and in fact, in the end, the repayment period was extended to infinity. Now, the functions which were laid on the corporation, I'll read these out. It had to do two main things. It had, one, securing, where the public interest requires, the development or exploitation of inventions resulting from public research. That means research was paid for with public funds. And any other invention, and that's any other invention, that's not a publicly supported one, which the corporation itself, in its own wisdom, considered as not being sufficiently developed or exploited in the public interest. Now, that meant that the corporation had to do something, if necessary, to secure development, exploitation, and licensing of results arising from public research. But if something else came into its vision, which was private, and it felt that something ought to be done about it, it had powers to do something about it. And in many cases it did. Note, for example, in the Holocaust. Now, the second function which was laid on the corporation was to deal in inventions, intellectual property rights, resulting from public research, and with inventions from other sources. In other words, that second function was just to look after the licensing of inventions, and that put into handling private inventions on behalf of people. The private invention part of it never came to very much. The only two I can remember of any great value were the Holocaust and the hydrogen oxygen fuel cell, which started off as a private invention. We became very deeply involved in that, and I was personally involved in that. I'm certain that the founding fathers who set us up were thinking primarily the corporation existing by licensing. Now, then there were the amending acts which went on until 1965, which extended the union. Now, I want to jog back a bit in time to before the Act and before the corporation came into being. During the latter part of the war years, there was a substantial drive, primarily by the Ministry of Supply or MAP, whatever it was called at that time, to follow up the work that was going on in the various research establishments to see if there were any inventions, new technologies emerging which could be protected by patent action and subsequently would be of benefit to industry. And I got involved in this myself for a bit towards the end of the war. And I was temporarily attached to the Ministry of Supply at that time from my parent department, which was the Board of Trade. And we were following up the work which had been started at TRE by S.D. Elliott and Tom Wilber, and was then going on at Manchester University. And that was felt to be a very important step forward in technique, important figures, which had begun to excite the informed people at that time, people who had heard about ECAC and other things, and knew what was going on, and thought this was all going to come to something very great. After I'd been doing this work towards the end of the war came to the end, I went back to my own employment, because I was on the examining staff at the Patent Office. But I hadn't been back there very long, and I was borrowed back again by the Ministry of Supply, because by that time the NRDC was on the verge of creation, and they wanted to get on with preparing this patent holding passed over to the NRDC. So I went back to them. Now, the NRDC was formally set up when the Act was passed sometime to get the dates. But within a matter of days or weeks after that date, and on the 28th of June 1949, NRDC was formally in existence with a managing director, Lord Halsbury, who was then putting together a board which ultimately had quite a number of prestigious people like Blackett and Sir Henry Tizard and Sponsor Jones, people that sort of names may be familiar to the old ones. And a small nucleus staff was brought together, and there were a very small number. There were two in particular. One was Dennis Hennessy, who had been in the signal during the war, and who was a patent agent who got involved in this Ministry of Supply patenting drive, and myself. We were involved with Halsbury on this consideration of what the corporation was going to do. Even before we had any offices, we were sitting in some rooms in the Board of Trade. Now, it was clear from the outset that the exploitation is now, by that time, quite a substantial block of patent rights or patent applications would be a major task for the corporation. It thought of it in terms of licensing. And that we hope that the techniques will be exploited by somebody, some sector of industry, but who, we didn't know. But there had been a significant event taking place actually before the corporation was formally created. IBM, having heard about the immediate access brilliant storage to work, got in touch with him and said that they wanted to know about it. Because although they were not seriously at that time contemplating becoming involved in commercial computers, they were involved to some extent in building some machines, you probably all know. Anyway, the result was that Halsbury and Williams went to the States, I think it was towards the end of 1949, and fixed up an option agreement with IBM for a license. And that, in fact, early next year was converted into a proper licensing arrangement with IBM when they had taken the decision to get on with the defense company at the time and the 700 series machines, which the early ones used for extended storage. Now that licensing arrangement was the first thing the corporation did under its terms of reference. And it turned out to be a very satisfactory one. We earned quite a lot of money from it. But we must not set up just to earn money from the Americans. We were supposed to be doing something in the national interest, and national industrial interest. So that we started to scratch around. And from the very beginning, Lord Hawkesbury was convinced that the exploitation of the rights held by the corporation, together with something which would encourage the building up of an effective computer industry in this country, was what he should be looking after. He wanted to do that. Some people would argue it was really outside what the corporation should be doing. But he didn't worry about that. And his solution, he said, the only way to do it, effectively, is to cause one of the major electronic companies to get together with some business machine corporation, either Power Sounds or the British Tab, and develop and build something and get it on the market. So he started a period of, I remember calling it in a paper I read at the time, this period of exaltation, when we tried hard to force some sort of joint venture activity with an electronic firm and Power Sounds or the British Tab. And this led to what was a painful period that lasted about 18 months or nearly 2 years, when we had working parties and study groups and all sorts of things and meetings with collections of industry. It all really came to nothing. Well, it doesn't produce any immediate results. And it was clear, at least clear to me in retrospect now, that the companies concerned in general were suspicious of NREC, suspicious of government interference. Neither did any of them, with one notable exception, really believe that there was a future of computers. And some of them are arrogant enough to say that, well, yes, I've actually got a record, it's been said. If it turns out that there is a these things, we, company X or Y, are quite satisfied that we could deal with it ourselves. Quite satisfactory. I won't go through all the torturous notes I wrote down here about the state of computer activity in the UK of that time. Anyway, it's notable that the first record I have of Hawkesbury enunciating this philosophy of forcing a juncture between two companies was made, and it's in the record, of the first board meeting of the NRDC, which was held in July 1949. Now, this phase of exaltation or persuasion, pressure or encouragement, something that Hawkesbury later referred to as time spent trying to push rules uphill. That's something I think he wrote in his farewell paper before he retired at the end of his tenure. That period lasted until early 1951. Now, by that time, things were starting. Discussions were emerging between the corporation and, on the one hand, Franklin and Elliott brothers about supporting something or other. Up to that time, Ferranti were involved in the computer business because they had contracts from the Ministry of Supply, I suppose it was then, to provide the engineering support for the team at Manchester University. This was some very far-sighted, a very far-sighted move by Ben Lockspicer, who was the chief scientist at that time. And he gave without any questions, tendered to Ferranti to provide these services to Manchester University. So that Ferranti were in the business, they were making machines, and we were aware of them because of our involvement with it. We were not particularly aware at that time of what was going on at Elliott Brothers, although we learned something from it as a result of all the various meetings that had gone on during the previous 18 months. Notes here about these advisory panels and things which I'm painting out. Lions, we also had contact from Lions, but they seemed to be quite isolated if we didn't want to know this. I think that another element, another impression that came out of me reading some notes I made at the time, was that Punch Card people weren't seized with the idea that it was a business application we were pushing for, and they thought that we were inviting them to do something to make a large scientific machine. Now there was another thing that happened which through caused some action. Towards the end of 1950, Walsbury was in the States again. I think doing something with IBM. And found out all that was going on the ground there. And was very impressed. And somehow or other got the idea, perhaps it was true, that there was a requirement, a government requirement, 10 machines in the States, which they wanted during 1952. And there appeared to be no chance of them getting the machines in time from any source in the States. And Walsbury thought, well, why don't we supply these? And there was a cable bombardment that was brought across the Atlantic, trying to persuade NSC and the rest of the tech in Tilney Street to try and get something done, get one or other of the firm making something, or developing and making something, to deliver 10 machines by 1952. It all came to nothing. The outcome of this was that Elliott's, according to my records, or Banquet anyway, did say that, well, we could perhaps do something, but we couldn't make what you want, which is something like the Ferranti Manchester University machine. We could deliver in 1952 10 machines according to our own present design. I don't know which one he had in mind. Anyway, that came to nothing either. But this resulted in us having much more exposure to what was going on at Elliott Brothers, and we saw all the work that we had described to you. And there was also the reference to something using Williams' tube, which made us pick up our ears. So it was still patent license oriented. And we were really very impressed with what we saw of their construction techniques. The end result of that contact was that sometime in 1951, I think it was, or it might have been the beginning of 51, we gave Elliott Brothers a small study contract to consider if their instructional technique could be applied to something like a re-engineered version of the Manchester University machine. Anyway, that led on to extensions of the contract and a number of reports, those machines which I would have heard about or resources. And in the end, a proposal was put to us for the development of a packaged computer. Now, the suggestion was that we should pay for the development and construction of the prototype. And this turned out to be the 401. And there was a sort of an outline specification suggested by them. As usual in these things, nobody could ever agree about it, would disagree. But we put the problem of deciding whether it was a suitable design for us to support up to the Brunt Committee. And I don't know if any of you will remember anything new about the Brunt Committee, but that was the DSIR Advisory Committee on High-Speed Calculating Machines, which had been set up by Ben Lockpfizer when he transferred to DSIR, as he set the committee up to monitor and look after the work that he had started in his contract with Frank. It was chaired by Sir David Brown, with all sorts of notables on it, including Hallbrook, and Professor Hartree and Professor Wilkes. And Professor Hartree never thought more than biology machines. Anyway, the result of that was the Brunt Committee, after not very long deliberation, came up and said, yes, they thought it was all right. Now that was good enough. We had some support, so we went ahead and gave the contract, gave Elliott the contract. We got that approval, because we had to go to the Board of Trade for approval on this thing. We got that by April 1952, but by that time the work was already going ahead and probably quite well advanced. We extended the study contract. Yeah, well, I think the estimated cost of this thing to start with was about £30,000, the whole job. And in fact, when we came to the end of all this, and the machine went off to Cambridge, and subsequently to Rothamsted, I don't think the whole thing would cost us much more than £50,000. This little aside about this, it was very interesting that in the arguments we had to get approval for this thing, and even internally in the corporation, there was a suggestion that by going to Elliott Brothers, beginning the contract, we were seeking up a competitor to Ferranti, who we by this time were also Italian. It's ironic that if it had been the other way around, people would have been chiding us for giving people unfair advantage. Anyway, now the other, I'll divert for a moment to Franti, because while this was going on, all three have been trying to get Manchester, the Franti people, to do something to develop a commercial machine. And that ended up with a fairly straightforward, quickly settled contract, whereby we undertook to purchase, pay for the construction of 4, originally and subsequently 6 total, copies of the Manchester machine, some modification, the Ferranti Mark 1 star machine, we contracted for them to make 6 machines for us, which we would pay, and they would resell them as arrangements. They had prices which we mutually agreed, which would give Ferranti their costs, plus profit of 7.5%, and a selling commission. And if we set the selling price right, we also bring back NRDC what it had spent plus some profit. And in fact, it did. It worked very well. Now, that arrangement with Ferranti was up and running before the 401 arrangements set up sometime towards the end of 1951. Uh, that the success with which that arrangement talked about and its results made us feel that it's a good way of going ahead to provide support, and we had no reason to believe that anything could go wrong. Now, we come back to Elliott Brothers, so that we got involved in supporting the development and prototype construction of 401. And you've heard, I think, it's been adequately covered without me going into details, or going, as I thought I would have to, and I'm dreading it, going into the analysis of what went wrong and the subsequent split. Now, all I can say about that to amplify or give coloration to what's been said already is that we were shattered when we first learned about Cole's departure, and even more shattered when it was clear that other people were leaving. Anyway, the way this was presented to us, or the rumours we picked up, or what we were told, well, I can't be certain about now, I don't want to be certain about, led us to the conclusion, particularly Baldry, and the members of what had by that time been created as a subcommittee of the main board of the corporation. This was the people subcommittee. I from my sin was the secretary of that. They were convinced that Elliott was just going to push it into the lower part, and what we had hoped would be continuing further development, manufacture and commercialization of something based on the 401 wouldn't happen. It couldn't happen. Why did we form this view so strongly? I don't really understand now. Anyway, we did. So that we were forced to the conclusion that we had to set up some rescue operation, which we did. And the story you've heard before. One slight comment on that. Looking through my notes, I wrote a paper in 1957 or something in RDC board, which summarised all we had done, with all the chronology and everything else, up to that time in connection with computers. And looking, I saw my copy of that, and looking over it, I inferred that although there had been rumblings about Elliott going to Frankie and so on, and Frankie possibly taking over the 401 technology, I got a note that this was raised by me or Bernard Swan at a meeting I had with him. Do you remember this? Do you remember that? Anyway, we'll come back to that later. Anyway, that all went on, and you heard the story of all that went on at Cambridge, troubles at subsequently at London, and Manchester. What subsequently emerged, of course, is that we were quite wrong in our forecast of what was going to happen there. Elliott Brothers went on from strength to strength and did very well. From some point of view, it's a great pity that we didn't somehow or other manage to hold the thing together and continue to support Elliott Brothers, because they may have been a much better base, a better location for a larger R&D effort, which might have led on to the next generation of computers earlier. We got to the next generation stage. Now, bit shocked because the contract had been set up, originally set up, with a ceiling on the cost of producing the prototype of 9 machines, so 10 machines for resale. That contract was set up on substantially the same terms as we had used for the Mark I star machine, that is, purchased by a corporation and then reselling for our agents, basically. And that I can't quite remember the figure now, but anyway, it was set up and there was a ceiling for the total cost of 10 machines written into the contract. Now you have to remember that these contract negotiations always tail well behind the actual work. I mean, we could go on with the job and we were still arguing about contract terms. We thought we got the thing settled. But we started to run into trouble because Vincent Franklin, when he got to know the terms, he said, I'm not having them. We were at the same time also having parallel discussions with him about supporting what ultimately became the Mercury machine. That came nothing to. But we were now caught in this track. We worked fairly well advanced. Couldn't possibly stop it and start taking work elsewhere. So we had to agree a compromise contract arrangement in the end, which struck out the ceiling on expenditure. But that didn't worry us very much at the time because we thought the figures we'd been given could be relied on. And it also did some other things about rights. We originally had a veto over the design change. This is really to safeguard the Strategy's position. But anyway, the contract was watered down and eventually signed. And then we discovered that the costs were escalating. There had been some overhead which had been lost, or something of this sort had gone on. And we were stuck with costs which eventually went to total 500,000 for this certain number of machines. Against something like about 250, just sort which we'd originally thought see. And of course by that time orders had been taken for 8 at least 8 of these machines at prices fixed on the basis of the earlier cost. And we lost a lot of money over it. There was a settlement at the end of the sort of that. I won't bother here into that thing. Yeah, yes. Yes, I think the rest of it is all stuff that will come out in discussion.
Could I now ask He and Mary to take us through the engineering side of Pegasus, taking our minds off of the more painful monetary and personality side of Pegasus, and look at the machine we all love.
Ladies and gentlemen, I'm uncertain whether I welcome this opportunity to celebrate the engineering genius of Charles Owen and the conceptual brilliance of Christopher Strachey, or whether, like pious Aeneas, before Queen Dido of Carthage, I've been asked to awaken ancient and unutterable feelings of regret. Regret that following the outstandingly successful development of Pegasus, the design team was disbanded, at least to my way of thinking, no worthy successor has ever been developed in Britain. With this in mind, I must first place the development of Pegasus in a historical context. And when I wrote this piece, I wasn't wholly aware how strongly the contributions of the speakers on Elliott's would colour what I had to say. Because I recall from those days when, like any other young engineer, I used to read the job advertisements. Those of Elliott's were always vastly more exciting and vastly more enticing than any other company that dealt with the electronic business. So that anything I say from here on out must not be taken to apply to Elliott themselves or their design teams. So placing Pegasus in a historical context and then identify a few of the individual characteristics of the members of the design team which had a significant influence on the design. I learned from my experience with Pegasus that good design requires reversal. But the prejudices of a single design authority require to be both articulated and respected. Problem definition is a vital precursor to problem solution. The successful design depends upon solutions with designability, amenable to design analysis and calculation. Since design is constrained by the limitations of materials, successful design goes, so to speak, with the grain. These were, in effect, the precepts on which both Owen and Strachey based their work. They were not, however, very typical of the world of electronics of the 1950s. What was this world like? The enormous impact of radar development during World War II was still much in evidence. A major advance in glass technology dating from about 1938, with the appearance of the Phillips EF50 valve, had fostered a succession of many moderately high-gain miniature vacuum tubes, only about an inch in diameter and no more than a few inches in length. Point contact germanium diodes had been developed during the war as radar demodulators, based on little more than the kitchen science of the crystal wireless sets of the 1920s. And with the invention of Shockley's point contact transistor in 1947, a hesitant semiconductor industry had arisen, concentrating on germanium semiconductor technology, hampered by the variability of point contact devices, and only marginally familiar with the technology of silicon and junction devices on which we all now depend. Electronics was still mainly the concern of telecommunications and broadcasting. The former with its 22-inch wide racks of equipment, 6 or 8 feet high, and the latter with racks as wide as 24 inches, at least in the BBC, bearing monolithic cadmium-plated steel chassis, each weighing tens of pounds, with a dozen or more valves and associated circuits. Significantly, most of those involved in the wartime radar development had been graduates in physics, without academic engineering backgrounds, since in Britain at least, electronic engineering was widely regarded as a dilettantic, not to say insecure profession, as I can remember very well, until well into the 1950s. This circumstance, together with wartime pressures, had confused the concept of design with the narrower field of circuit design, and established a widespread design tradition of suck it and see whenever a problem arose outside the immediate experience of the designer. That's not to say, as a speaker said this morning, that suck it and see was how circuits were designed. That depended entirely on the probity, the intellectual probity of the designer. But suck it and see was still very much the way of dealing with any problem which was not immediately in the competence of electronics. Again, where the logical power of electronic digital computation had been clear since the early 1940s to the indoctrinates at Bletchley Park, it was the domain of a smallish band of mainly academic successors, among whom few had studied design as an engineering discipline. Even where, as in the BBC engineering departments, numerically based design was given its full due, on the electronic front, this was in the context of high-quality analog circuits, made linear with a quasi-statutory 40 decibels of negative feedback. Consequently, there was no pressure at all on the makers of valves or semiconductor devices to publish the variances of the device parameter data. To the contrary, it was rarely clear whether published data represented design targets or achieved median values. Lastly, despite the marketing hype of the recent Festival of Britain in 1951 and the governmental initiative of NRDC, there was no longer the recognition of engineering as an important aspect of the British Raj, such as it had existed in the 19th and early 20th centuries, when it was natural for consulting engineers to establish themselves in Victoria Street in order to exert both proper and improper influence on Parliament and the ministry. Turning now to the major players in the design of Pegasus, these were four in number: Charles Owen, Christopher Strachey, Brian Maudsley, and myself. Those of you who came to this morning's session will have heard something of Charles Owen's influence on the restructuring of complex electronic devices through the development of package techniques. I would like to add my own tribute to his engineering sagacity. He had the essential vision of a successful engineer, which is to have formed an architectural concept of the finished work from the earliest possible moment. Changes to that concept could be made as the design progressed, but any change had to be demonstrably beneficial and to meet Charles's exacting standards of acceptability. Given the clear benefits and the conformity with the standards of acceptability, there was, in my experience, no need for further persuasion. It was stimulating to work with someone who had no need to reinforce his prejudices with anything but logic and good sense. In addition, Charles was very ready to pass on his own knowledge, a characteristic which endeared him to me, as I had had no previous experience of digital techniques. With all of that, and though often doggishly witty, Charles was essentially a plain man for whom facts were facts and fancies were fancies. Christopher Strachey, on the other hand, was a modern Renaissance man. Besides his achievements as a mathematical logician and systems conceptualizer, he was a most talented musician. He and I used to sing and play together. And his skill in technical discussion or general conversation was such as to make everyone else present perform beyond their usual level, as a consequence of his own rather competitive verbal brilliance. The third principal member of the design team, Brian Maudsley, was unusual in both background and in personality. A mechanical engineer from Ferranti, Edinburgh, fallen among intellectuals, he held his own in consequence of a unique capacity for mechanical innovation and for mild-mannered, unarguable assertions, all supported by a physical stature of 6 feet 8 inches. As for myself, I joined Ferranti from 4.5 years in the BBC Engineering Research Department, where I had worked on a number of electronic and electromechanical projects connected with both disk and magnetic recording, and where I had encountered many of the problems which were still then an issue in the Pegasus project. My only previous experience with digital circuits had involved telephone relays of the type most of you will be familiar with. We called them post office relays. A brief encounter which left me with no yearnings for further involvement in relays. We come now to the design principles on which the architecture and design of Pegasus was based. Strachey's major objective was to reduce the labour of the programmer, especially by providing an efficient and consistent order code. By freeing the programmer from undue concern with machine architecture, by minimising performance bottlenecks, and by maintaining an autonomous invigilation of all machine functions using odd parity checking throughout. Owen, for his part, had an intense preoccupation with machine reliability and availability. His experience led him to believe that while this required conservative design, with care, this did not get in the way of achieving elegance and economy. Both he and Strachey aiming to build all of the complex control functions without recourse to special purpose circuits. With both prudence and modesty, he took the view that the basic circuit elements used in the Elliott 401 represented the soundest basis for progress. Packages containing several configurations of point contact diode and gates, logically ORed, followed by a cathode follower direct output, or an inverter, or a simple pulse amplifier retiming and delay circuit, furnished the logical armory for the bit-level logic, as in the 401. While single-word packages using a nickel delay line as the serial storage medium provided immediate access memory for accumulators and registers. Now, it's fairly obvious that the more complex a logical function, the more numerous are likely to be the various inputs. In consequence, one requires that the number of inputs to individual AND gates should be as little restricted by circuit component deficiencies as is prudent. In upgrading the Elliott logic circuit, Owen instituted a statistical analysis of the problem, having ascertained by experiment the variance of the germanium diode back leakage resistance, and so avoided the Scylla on the one hand of AND gates with the more leaky diodes exhibiting pattern-sensitive failings, and the Charybdis of overly restrictive gate design. Jumping ahead a little, I would add parenthetically that in my part of ship, and before my arrival on the scene, Owen envisaged a nickel-plated drum similar to those favoured by the Ferranti Computer Department in Manchester, with a minimal complement of read and write amplifiers, using those aforementioned post office relays to access individually selected read-write heads. The binary sequence would be recorded using phasing coding, whereby a series of ones was a more or less square wave of magnetization in opposite phase to that for a series of noughts, while alternate ones of noughts was a squarish wave of twice the period, as shown in the diagram. More of this anon. In considering the remarkable success in achieving all the design objectives, I would ask you to remember also that Pegasus is a serial machine in which the 39 working bits of each word arrive sequentially at any point, or as we now say, at every interface in the machine. And to maintain the economic advantages of this serial approach, interface width has to be kept to a minimum, nearly always only 1 bit wide. The parts of the machine where static registers hold a number of bits of a word concurrently are thus few in number. The thinking required in the logical design, particularly of the control functions, therefore, requires the designer to envision successive machine states represented by circuit states changing autonomously and much faster under the inexorable flow of serial data. This is a duality which it is difficult to represent conspicuously in any diagrammatic form, and was quite beyond the descriptive mathematical techniques of the time. In this regard, I well remember the seminar when the logical designers first gave an explanation of the control architecture. By then, Pegasus was in active use, and the logical design seemed to be consistent. But for my part, at least, the description of the various control cycles remained and remains baffling. Coming now to the engineering problems which had to be solved. We can regard them arising against three design aims. And I'd like to put on the slide. Fine. These are reliability, economy, and performance. Past experience had shown that the major areas of transient unreliability were pattern sensitivity of individual logic or storage units, where corrective operation continues until a particular sequence or gate input of binary digits occurs, which evokes an incorrect output. Secondly, drum systems generally. Think of a difficulty and they appear to have it. Thirdly, package plug and socket electrical contact variability. And in a moment, I will address these areas in reverse order. Happily, by this time, other electrical component deficiencies did not present as causes of transient problems, and were adequate in terms of operational life, given that they were not sourced from suspect quarters, such as government surplus, a false economy which has bedeviled some other projects. Now, except to a mechanical engineer of particular discernment, there is little intellectual stimulus in addressing the problem of erratic plug and socket behavior, which is why the problem, I think, hung around for so long. In many ways, this was the most dangerous of the package circuit problems, since so many package interfaces were at risk. Maudsley tackled and solved it with determination. To keep the contact resistance of each contact adequately low, he insisted that it was insufficient to rely on the comparative incorruptibility of noble metal surfaces, and that on each insertion of a package, every female contact should scrape its corresponding male and ensure a new metal-to-metal interface. Given an adequate thickness of noble metal plating of the male contacts, a quite adequate, if limited, number of insertions would be made. The female contact was of that shape seen in plan, and of that shape seen a horizon. And when the board was inserted, there was a slack twisting action and a scraping action. And if you look at any of Tony's packages which are still in use, you can see the scraping of new clean metal every time a board is inserted. It might have seemed a risky way of proceeding, on the basis that noble metal surfaces can get worn away very quickly. But in fact, we reckoned that we could do at least 50 insertions without trouble. And that was well beyond the number of insertions one would normally expect a package to receive. The inline multi-contact socket used had the necessary female contact geometry as I've shown, and a concomitant to this solution was the provision of a robust and stable mounting for package board and socket, and that is shown in sketch form in the second part of the slide. This was achieved most economically by the use of aluminium alloy die castings for the package shaft mountings. The robust behaviour of Pegasus after switch on and throughout the life of the various machines has been very largely due to this solution to package structure and contact geometry. Lastly, of course, the package board itself had to be of an adequate rigidity and stability, and you'll understand, of course, that attention to the details of this sort have not distinguished previous computer projects. My own partnership, the drum system, appeared to present problems in every possible area. The geometry of the magnetic fields causes the head signal to be rapidly attenuated with an increase in the read head recording medium gap. The functional relationship has been established by a research worker in Holland while I was at the BBC and is shown in the diagram. The read signal is proportional to e to the minus 2 pi d over lambda, an attenuation function like the side of a house. It results in 56 decibels lost in the wavelength of separation, or about half the signal is lost in geometrical progression for each extra tenth of a bit length gap. With a drum diameter of 10 inches and 128 42-bit words per track, we had actually more bits per track, bits per word. We had 42 bits per word, not 39, because of 2 separation bits and both a parity and a sign bit. It turns out that an overall variation in signal of 2 to 1 ensues if the radial run out of the drum surface due to machining tolerance, variations in coating thickness and bearing shape is no more than about half a power, and exponentially pro rata. Owen had already decided this was too demanding by a factor of 2, and had laid down that alternate bits would be recorded in pairs and tracks, so that we could have double the wavelength for each bit. With the write and read head diplexing, handled by machine logic, a strategy previously adopted at Elliott's. I soon realized that not only the diplexing, but also the actual phase-encoded waveform could now come directly from the logic. A drum 1 being written by a logic 1 input to the left-hand side of a push-pull amplifier, followed by a logic 1 to the right-hand side, and vice versa for a naught, first on the right and then on the left. This removed the need for a special purpose circuit, pleasing everybody, especially me. However, even a total run-out tolerance of half a power appeared to have caused difficulties with previous varying design and varying life. And there was some disquiet in connection with the drum under development at Ferranti in Manchester for the forthcoming Mercury computer. At the BBC, while studying the problems of television magnetic recording, I had tackled the problem in the lab by using a horizontally mounted narrow drum, or disc, with a little-known 360-degree varying design. This had, however, to be hand-lapped to a radial consistency of about 1/10 of a power, and the drum surface with its magnetic coating was then sapphire turned, which was easy for us as we're in the recording section. A 360-degree bearing is nominally permanently lubricated. It's not a loss bearing at all. But it works best with a lubricant with particular physical properties like sperm oil, which is a bit bizarre. And I introduced this with an eyedropper to my own machine. Maudsley, very properly, would have none of this quasi-magical 19th century engineering, and quickly came up with the solution. He said precision boring spindles had to perform with a radial run-out better than a tenth of a power, without adjustment over a period of many months. So why don't we approach a manufacturer of such machine tools and give him the problem? And that's what we did. Bill Boner of Boner and Turners in Mansfield cheerfully undertook to make a suitable drum mechanism if we provided him with an outline design and details of the motor to be incorporated. The final outcome is shown in the diagram, and you'll notice that Bill entertained no unnecessary taboos or superstitions about putting 3 bearings on one shaft. And he assured constancy in bearing behaviour and length of bearing life by using twin sets of angular contact ball bearings under considerable axial pressure. As I recall it, the original prototype which we used in the first Pegasus cost only £300, excluding the electric motor. Please note, however, that the drum fitted to Tony's machine in the museum is a later and larger version, although it's built on precisely the same principles. Now, other Ferranti drums were run as slaves to the rest of the machine, synchronized in a phase lock with the crystal-controlled logic circuits, requiring an elegant servo system, and culminating in a very hefty power amplifier. This was, in my view, to turn good design on its head, because you are making a cumbersome object, a rotating drum, slave to a more pliant system, a lot of digital circuit. Our drum needed over 1/4 horsepower, making the scheme doubly unattractive. I therefore got Owen to agree that the logic should be driven from a top track recorded on the drum, while the rotational speed of the drum could then be kept within the limits required by the delay lines, using quite a simple servo loop with a crystal reference. As the drum drive had to be at 150 Hertz for the 4,000 revs per minute rotational speed, this loop included the motor excitation of the 150 Hertz alternator set. That left us with a small problem. How do you record top track on the magnetic oxide, which is consistent, the right number of bits, and actually joins without any bumps? We accomplished this by first recording an approximately correct but incomplete clock track, which was then very temporarily phase locked by hand adjustment of the servo at the correct rotation speed, using a crystal controlled reference and using expanded trace oscilloscope. The rotational inertia of the drum made this practically possible without any excessive manual dexterity on the part of the operator. A burst of clock frequency of the correct length to close on itself was then recorded. Ferranti drums had previously been nickel coated, as I mentioned before, because the low coercivity required little power output from the right amplifiers. However, these coatings had occasional magnetic weak or dead spots, owing, I believe, to stresses in the plating. Subsequently, when I went to IBM, I discovered they'd had similar problems at about the same time with their drums on the IBM 650. And they eventually overcame them with weird chemicals in the plating bars. At the BBC, however, I found that Epi-203 magnetic oxide dispersion, used for coating magnetic tape, was readily spray painted onto a drum using just an ordinary spray gun. And so he abandoned nickel for red iron oxide. Split rings of low-loss ferrite had also worked well as read and write heads, up to well over half a megahertz, 500 kilohertz. Needing using only pairs of miniature power pentodes to drive the magnetic oxide to saturation. Better still, correctly formed ferrite recording head blanks were then becoming available. And I was fortunate in finding a subcontractor, Epsilon Limited, making multi-stack heads for tape recorders who were willing to package banks of ferrite heads with a low impedance to my requirements as shown in the diagram. That's an isometric for one head and a stack of them, and two stacks mounted on the mounting block as actually used in the drum. Drum system performance and reliability, usability, was greatly increased by abandoning relay head switching and developing valve and germanium diode crossbar switches for writing and reading. I will confess in public that the thought of finding how to actually design multiple post office relay systems was something I couldn't face at the time, and it was simpler to do a bit of reading. The consequence of that was I found this circuit in a technical journal which, sadly, I can no longer identify. I don't, in actual fact, think the author had used it. It was merely an idea. But this is one vector of a crossbar, and you select a particular recording head by energizing one of these supply points for the HT valves. We did find, this was not in the original design, that it was necessary to put those extra diodes in as clamps to prevent crosstalk occurring between the selected head transformer and the unselected. The reed switch came before any amplification and was entirely novel. Charles Owen had to be convinced by a test lasting several months with a random batch of diodes that diode noise would not cause errors. However, diode noise remained below 250 microvolts, which is quite harmless to the unamplified phase-modulated signal from the heads for some 3 or 4 millivolts. These switches meant that the relay switch settling times at 20 milliseconds, which is what you get in the post office relay, were totally avoided. In fact, the reed amplifier recovery after writing time of about 500 microseconds became the limiting factor, while track switching took only about half that time. For those of you not familiar with old-fashioned electronic diagrams, I should point out that that transformer and that transformer are two of the same transformers that you saw on the right amplifier diagram. They are the identical transformers, if merely a third winding of the transformer that is shown. So we both improved the performance and enabled single word as well as 8-word block transfers to be efficient. Lastly, block addresses in the drum address track were permutated to leave 2 blocks between blocks with successive block addresses. Within any given block, word addresses remain in natural sequence. This gave time for some computation between successive blocks without involving the programmer. He didn't have to go in for fancy addressing in his data. A technique which I regard as utterly fearful, which has been mentioned earlier today, optimum programming, which was in general used for other drum systems. In consequence of these innovations, the drum system became uniquely in harmony with the general approach that distinguished the Strachey own design. There is, I'm afraid, only time to mention two other features of the logical design that contributed to overall performance. These were the provision of multiple accumulators and many more registers, and the incorporation in the order code of a comprehensive and logically regular method of handling address modification using some of these extra registers. How much more effective would Pegasus contemporary, the IBM 650, have been with these features, designed as it was for similar user areas? How sad that Pegasus could not have been equally widely exploited. That concludes my survey of Pegasus development, except to say, as I wrote in the Computer Journal of June last, it is a matter of record that all of these features were working in the Pegasus pilot by April 1956. In fact, Hugh told us they were working by March 56, and he's probably right. Developments begun in 1955 added card and tape peripherals in the subsequent years, leading to machine sales of nearly 40 machines overall. Regardless of these good beginnings, an evident loss of focus on the part of the Ferranti senior management, coupled with NRDC's short-term financial preoccupations, fostered an atmosphere in which by 1956 the burden of continuing investment was only acceptable at a level requiring a fundamental choice between the Mercury team in Manchester and the Pegasus team in London. Except for the peripheral developments mentioned above, the Pegasus team was largely disbanded, and staff were redirected to work on Ferranti contract and defence work, or in the case of some of the leading team members, regrouped under American auspices in September 1956. This was a blow to the infant British computer industry at a most crucial time, from which subsequent events have shown it never wholly recovered, exemplifying how inadequate investment ensures a net and enduring loss. The history of Pegasus has always seemed to me to be a paradigm of the British industrial malady. Not just the shibboleth of the past 30 years that Britain fails to market its wares, but more fundamentally, that we no longer recognise or foster, and therefore cannot exploit, our real strengths. And I must thank the Science Museum, and particularly Tony Sale, for the opportunity of making a contribution in celebration of this particular technological period victory. My thanks are also due to Professor Elliott for his visionary leadership in assembling and managing the team with which it was a joy to work, and for the lifelong friendship which has ensued.
We will now have a short tea break, half an hour, same place as lunch, upstairs.
Our Office Administration Department in London was also investigating possibilities. And in 1954, they sponsored a visit to the United States to go and have a look at what they were doing there. And I spent 6 weeks there, one of which was on a course run by IBM, of course. And the rest of the time was spent visiting other industrial organizations who we had heard were either got a computer or were about to install one, and to learn of their experience. And it was, again, a very interesting trip at that time, and I came back with one or two lessons I thought, conclusions. One of them might strike one as strange now, but in 1954, that visit convinced me of the viability of magnetic tape as a computer medium. It also drew to my attention a company over there, whose name was to crop up in negotiations with Ferranti. I also, of course, was impressed with the fact that they found it far easier to justify commercially on financial grounds and installation by virtue of a much higher salaries, technical salaries. So they had to save about half the number of people we might have to do to demonstrate to their board that it is a viable proposition. And in those days, as I think in these, my company wasn't very interested in spending large sums on computers for the pure purpose of experimentation. They demanded a financial justification. So I had to try and seek one. Just before going to the States, I decided that we put our feet in the water slightly by ordering an electronic machine, another general purpose computer. And this was the Holrose 550 calculator. It was a limited success, insofar as it did what it purported to do, and did it well, and did save us some time and effort. But of course, it did not give us any feel at all for the possibilities of the general purpose computer. So, however, I found our research department also carried out investigations, and for this purpose, I had delegated their investigation to a very able young mathematician. Man, as came to be mentioned today. And they had come to the conclusion that they could see no great use for a computer in their department. They might be able to make use of one for a few hours a week. Incidentally, we've already been spoken of the use of computers for plant control, etc. And I, again, talking to our engineers and our works people about it. And I can always recall one works plant maintenance man engineer saying, put a computer on to control the plant. He says, damn it, I can't justify a new temperature recorder. So he didn't think he could justify the then going price of perhaps £50,000. However, the board were gradually becoming interested, and the research department and I presented a joint paper to them. The result of which was, yes, they gave me sanction to expand our investigations beyond my individual department, and the research department seconded this mathematician to me, Alan Kay, to assist in this venture. He eventually became my chief programmer and eventually went on to become the operations manager of the Iceland installation. So we looked around, and at this stage, of course, one of the things we discovered was that the general purpose computer was becoming understood by many, and particularly its apparent possibility of answering all sorts of questions always was right, because it aroused a Luddite feeling, not merely now in the junior level, but amongst managers who felt that their jobs might be threatened, their status threatened by this peculiar instrument, and the person who controlled it. It was not the hand that rocks the cradle, but the hand that controlled the computer ruled the company seemed to be their approach. And so I found myself not greeting friendly in some departments, and I sought to investigate them as to any possibilities. However, we reached the stage when I was able to put forward a draft paper, and my chief finance director said, well, look, it's all right putting up new papers, but you're not going to get a blanket sanction for X thousand pounds to allow you to go out and choose any old computer you then like. You better come up with a specific proposal. So we started examining all the choices that we saw open to us. And sent off my programmer on to various courses so that he could get to know the various machines. Not all of them, but the machines that we considered at the time were the Hector, the Lion Clear, English Electric Juice, Data Corporation was Datatron. It was probably Electro Data Corporation that convinced me more of the viability of magnetic tape than any other. The other was the IBM 650, the Elliott 405, and the Bernanke Pegasus. Well, we ruled them all out and eventually except the Pegasus. And we did it on these grounds. We made this up. The first three we ruled out fairly quickly on the following grounds. None of them had any provision for the use of magnetic tape with their equipment. The whole effect core we considered too slow and probably limited in its capacity and generally rather poor design. The Lions equipment, apart from not having magnetic tape attachments, we didn't consider the company had a future in the computing field and would therefore be able to keep the rest of the developments. So we ruled out. English Electric at the time didn't seem very interested in the commercial data processing, and again, their machine didn't seem to be appropriate to the commercial user. So we ruled that out. English, the Electro Data Corporation machine we liked very much, but again, we ruled this out because it was already a higher price than either the Bernanke or the Elliott equipment, and that price would be further inflated by customs duty. As they'd no associates or any staff in this country, we would have had to take responsibility for installation and maintenance ourselves, and we'd also had to send programmers to the States to learn programming. So that was ruled out. We also at the time felt that we preferred to buy British if we could. The IBM 650 was ruled out, not because it was American, but because we thought that its advantages of being tried and tested equipment at that time, and the fact that it did have this large IBM organization behind it, were not sufficient advantages to justify its relatively very high price compared with this other equipment. Instead, I think came to the opposite conclusion, and in fact, ordered and installed the version of IBM 650. The other advantage which it now actually said to have had was that it was a decimal machine. But we felt that that was not a great material factor, since at that time we worked in LSD and we had a conversion factor whether the machine was decimal or binary. So we didn't think that was a great factor in its favour. So we finally decided our choice lay between the Elliott and the Bernanke equipment. And we tried to make a detailed assessment of this. Programmer went off and did a study in depth as far as he could on both machines. We learned from other speakers of the design of the Pegasus, speaking of Mr. his contribution to it, from the point of view of making it easy for the program. This certainly showed up as my chief programmer became extremely enthusiastic about the Pegasus, and after his enthusiasm and conviction to me that it was a better machine from the programmer's point of view. Another factor which did influence us, and certainly influenced my director, was the proximity of the Bernanke factory. Namely, that it was near enough for us to expect rapid response to any problems, maintenance, etc. that we might run into when it was installed. And as you can imagine, a chemical company with lots and lots of parts is rather experienced in problems of maintenance and components. this stage, of course, Pegasus didn't exist. It wasn't the London machine, I don't think, at that time. And certainly it didn't exist with magnetic tape units installed in by line printer output, etc. So I then asked the perhaps if they could catch all this stuff and make it into a data processing system. And they said, yes, no problem, we do it. So we also replaced an order. Because the interesting commercial fact is we actually placed the order of the Pegasus with them until we actually got it. New to procedure perhaps, but my purchasing department stopped buying it, very pernickety, and they didn't place an order until they could specify it precisely, so that it agreed with what they agreed with what we ordered. And we didn't know what we were ordering precisely. They said no, so I placed a letter of intent. During this period between letter of intent and delivery, we held regular progress meetings with the engineers, etc. These were most frequently held in London. Sometimes, however, in Manchester, frequently in London, where, as I say, we were demonstrating his great knowledge of my art. He also demonstrated to me his further esoteric knowledge on the directions, because it was a large branded team that at each time. Most of them, when new faces appeared, and usually they'd be introduced as so-and-so, he's an expert in this, that, and the other. However, one time, as was left in there, I've never seen before, and he wasn't introduced as representing a specific body of knowledge, and he made contribution to discussion, frequently very good afternoon. And afterwards, in my pub, I asked Bennett who he was. And he said, do you know anything about sticklebacks? And I thought, well, partially from the end. I said, what? I didn't know. Well, if you had a bucket of sticklebacks and pour them into a pond, they'll divide into two. One arm will go one end of the pond and the other to the other. And there they'll build a nest. Then they will venture forward from that nest toward the center until they meet resistance. As heavy as a stickleback. To this day, I'm not quite sure what that is going to do. Representing. But during these discussions that we perhaps made a contribution to the eventual design in some senses, we had of course specified magnetic tape, card input, etc. And in one of these meetings, they suggested that they would prefer not to link the punch card input and the printer output directly to Pegasus itself, but rather have a converter unit. And the converter unit, which would be attached, card input, printer output, and there could be a simple mechanical switch transfer tape unit on which control. So we would have 4 tape units, and as long as we didn't need 4 source purposes attached to Pegasus, we could switch one over any of them to control this converter unit. Would we accept that? We discussed it, and we could see advantages in it in the operational view, which were proven eventually as we agreed to it, and that's how they designed the system. The converter unit was almost as big as Pegasus itself, and it was a real Kleinwood setup. It had a Holroyd punch card reader, a French normal printer, and a practical converter. And one of the things that again influenced me in moving to Pegasus was that they had undertaken to fit Electro Data Corporation tape drives. Because I got some confidence in those people. I thought this was a plus for this system. So that was the system that was eventually settled upon. The converter, separate converters enabled, of course, to be reading cards on magnetic tape, or printing magnetic tape on cards, while at the same time die, the customer sent in a piece of plant and said, I want the precise die I've got to match this for the customer. And many people down there, and of course, it's almost universal in the diamond and world. The other facet of it that was influenced by us was the refrigeration of Pegasus. There were all these discussions. I had with me one of our own engineers who was responsible for the area in which the computer would be. He was our maintenance engineer in charge of all maintenance work in the area. And as Edith said, in this is going to generate an awful lot of heat, aren't we? Good. And so around the time I got in touch with the refrigeration engineering firm, we just designed a refrigeration system that would go around Pegasus. Later on, they suggested that we should keep our magnetic tapes here in a controlled temperature, and I got together this refrigeration engineering firm, and one of my then people remember from Chicago accessories, Ross, and they together designed a refrigerated cabinet for the storage of magnetic tape units. Well, during this time, of course, to the document beyond what it had been, it was similarly, but it was eventually delivered. Installation took a long time, give it pass and acceptance test, etc. And again, I remember very distinctly one of the engineering characters displaying his enthusiasm for computers by saying to me that, you know, while he was tackling a fault, these things should never be handed over to customers. It's too interesting. He loved his golf. And it was finally installed in 1958. 1st of May, I think, was the official installation date. It then worked happily for 5 years. From the first year, we had one or two early incidents, one of which was the snapping of magnetic tapes. But my operating programmers always seemed to manage to get the tape instruction never again, and we never lost any information. But it did suffer one period from lack of preventive maintenance, and my own resident engineer, who was in the room here, drew my attention to this. Very granted, he would accept it, was getting all the attention it needed, until finally it did behave off disastrously, and they sent round the senior maintenance engineer, who took the covers off and he scanned overall, and he said, let me find out any dry joints, etc. And he turned to his team and said, get it working now. You've got 3 days. The refrigeration incident is useful another way, and I was slightly embarrassed showing some of the directors around. I opened the back where the drum was to show them the drum housing. There's a bottle of milk. System extremely useful for their bodily needs. However, it was used for 5 years, during which time we developed many new uses, and after getting onto it, all the sales analyses, etc., we concentrated on applications which we couldn't do manually, but which would give us better management information. For example, dyestuffs, then, not dyestuffs anymore, not that cool, but has literally hundreds of products sold in almost every country of the world. And one of the things that it didn't know, difficult to do manually, was the profitability of any single product in any particular country, taking into consideration carriage, insurance, etc. So we were able to devise a program which would produce this information. That was regarded by salespeople as a very vital way of new information. experience of it, other than to say that in the report I wrote 5 years afterwards, and to demonstrate its financial viability, it had suffered, and we all suffered in those days, from the slowness of programming by comparison to those methods, and therefore the slowness in getting applications on. But despite that, the machine showed a profit over that period, and we had got a number of extra good management projects out of it, and a certain amount of technical work, all for free, paid for, as it were, by commercial users. So on that note, Chairman,
Harold Gearing talked about the use of his metal box stopper. Very rapidly.
Mr. Chairman, ladies and gentlemen. My first 7 years was spent in an accountant's office where everything was manual, and I well remember having to spend several weeks getting out ledger balances at the other end. In industry, I found that to get the best out of mechanical accounting then available, we first found out exactly how they worked, prepare the program control bars and wired connection boxes oneself, get maximum use of facilities. In the Metal Box Company from 41-42, which developed centralized sales ledgers and cash collection, and a very extensive sales analysis covering eventually 26 factors on power Salmer's punch card equipment. We acquired additional sorters and tabulators to expand our Worcester installation with the growing post-war expansion of sales. On coming back to London, I became connected with friends from pre-war who were working in the computer field. And I gave some evidence to the computer of the NRDC in June, Computer Committee of the NRDC in June 1950. And in that evidence, I stressed that any commercial version of the punch tape machines then becoming available would need to have punch card input, an unlimited backing store in the shape of magnetic tape, which could be sorted and resorted as much as necessary, so that one had an infinite backing store and line printer output. To assess in detail what the various new machines could offer, like Cyril Wilkes, we've sent people on various programming courses. And including Leo, Elliott 405, Use, and Pegasus. The Pegasus interested us because of the ease of programming, and we did some experimental work which I wrote up in the Computer Journal in April age 61, covering a market survey completed within 5 weeks, experimental sales forecasts with material equivalents, and some quality control analyses of variance of raw material. In August 1958, we gave a letter of intent to Franti to acquire a Pegasus system subject to satisfactory card input, magnetic tape with sorting programs, and line printer output. We acknowledged the help of Franti, Biswa, Northampton College, and others who allowed us to use their Pegasuses for ongoing sales forecast and other work, including programs in AutoCode from other departments in the company. Thanks to the efforts of our resident Power Salmer's engineers, helped occasionally by having access to a local tool room, our tabulators were kept going well beyond their expected life. During 1958, the first half of 1959, our experimental work on Pegasus continued, helped by being able to use other organizations' installed machines, and we noted in use a Sirius machine in London, with which the Pegasus AutoCode had been adapted. We briefly considered a Perseus installation. By July 1959, I was able to report when I board that 25 Pegasus computers had been installed, with more programmers apparently using them than on the other UK-built machines. Magnetic tape had been working from June 1957 with sorting routines developed. They had advanced initial orders, parity checking of all internal transfers and data and to and from tape. And with ICT had developed a universal 6580 130-column card reader without plug boards, which permitted the user to have several different card layouts of the same physical column numbers, identified by codes and program in any one computer job. Line printers were under continuing development with other manufacturers. They had a growing library of application programs. All that I asked for in 1950 now seemed to be available, and we had placed a letter of intent for Pegasus, but in November '59 I announced the multi-programmed Orion system, which promised to allow several jobs slow and fast, including programs under development, to run together without any risk of clashing, thanks to the Orion Monitor program and relevant engineering based on an article originally written by late Stanley Gill, and developed by George Felton and others in the team. We switched our order to an Orion, missing our turn to get one of the early machines because of the delay in getting approval for the increased expenditure. Some of the initial applications were further delayed by the delay in developing the promising nebula business data processing multi-code. Our Orion was delivered in April 1964, handed over in July 64, and I regard Orion as a postscript to all the Franklin Pegasus development. Other users, particularly bigger shipbuilders and cabarets, made use of it, as well as ourselves. Our main applications are running by 65, 66, and I claim to have had one of the first open item sales ledger systems on magnetic tape on the 1st of April 66. I visited the USA and France in 56, and I had also been impressed by electrodata, as was Cyril Wilkes. Again in 1966 I visited America and compared our delayed progress with our associated companies. In 1966, in New York, April, IBM was still talking about time sharing, but could show me no 360 installation able safely to run several programs with full accounting of value used. I had had this in my office for 18 months. Open item statements were still on punch cards in the United States because that was the only way they could see a plucking the paid item, whereas we had developed a method of numbering them and taking them off magnetic tape. Ferranti, developed from Pegasus, had clearly had a world lead in my view at that stage. Orion continued working 3 shifts, taking on 4 times the original powers load, including payrolls and factory machines, using standard telephone punch tape links, punch paper tape. By June 73, when it was switched off, the Orion had operated for 8.5 years, had operated for 26,561 hours, and passed all its data files eventually to the ICL 1905-4A via the link. I handed over the computer management in August 1973 to New Blood to improve the data input procedures, and have since developed new systems online to branches. I have seen over a period of 45 years the whole transition of accounting work from laborious pen and ink to true automatic time-shared data processing, and I regard Pegasus as being in the middle of all that development. I would not like to go through some of the frustrations we experienced again, though I am currently able to amuse myself seeing the background of what really happened from the Computer Society archives here, where I've been invited to help classify them. On the archives, we would like to have some sponsorship to get them fully recorded on the paper tape so that their record can be available to future research students. Thank you, Mr. Chairman.
Right, I'll ask Professor Elliott now then to take up the more general discussion.
We'll deal with the last 2 items on the agenda as well. The what if questions will roll into the general discussion. I'd like to give myself the slight luxury of being a little anecdotal. I'll give anecdote. I'm sorry I don't see Lance 12. He's got. Oh, good. I just wanted to remind him. He spoke of his being sent to Elliott Brothers for a work by the appointments board. I remember the day he arrived and reported to me. And he's the first person outside hotel quarters who brought me up with a staff by calling me sir. I'm pleased to see so many other people, former colleagues, and to those from Elliott Brothers who were there when I was, I wonder if they recall the little gathering that was addressed by the head of electrical engineering, Harry Gale, a few words upon my departure. He was carrying a large package, which obviously was to be a party gift for me, very large it was. You heard about the relationship between the computer division and the electrical division about printed circuits. This large parcel was unwrapped and handed to him. And lo and behold, it was a large, that size, printed circuit. And I want to thank those people again, because it still is in use in my house today. A very durable printed circuit. Not only that, but I discovered about 15 years later from a friend that Harris marketed then a trolley on which this printed circuit could be placed and becomes a heated trolley. Thank you so much. Now, to be serious, several people have spoken quite glowingly about the undergraduate. I agree with that. And people have spoken very glowingly about John Coles. And one of them has said clearly they were poles apart. Now, I would like to ask, perhaps John Crawley might comment on this, whether the effort to progress matching or putting an electronics firm and a punch card firm together really paid off. I'd like to suggest, or wonder if NRDC had been able to spot that difference, that tension between Coles and Bagger, and do something to either ease the tension so that there wasn't a blow-up. Maybe, if he was going to Cambridge, let that be known and take steps to organise for his departure. I just wondered that. It was said by Lawrence that they had great vision, Ross and Bagger, which could have served the UK well if only they had had the commercial and financial stamina to carry it through. Would it have been possible for NRDC to stop that explosion and continue to support Elliott Brothers so that they did have the commercial and financial stamina to carry it through?
Well,
just a minute, sorry. We've been talking about the two firms. The other firm, NRDC, found that there was a difference between them and the firm because the managing director, Vincent Brandy, did not want to risk the family money. He did things because they were interested, and that's all. So they didn't go on supporting computers. Could NRDC not have spotted that situation and done something about it?
well, I think it's possible that we might have done so. In fact, we didn't. I think we were so excited at the time. The goal of driving on the curve or producing something of that sort. We saw the possibility of getting the 401 out and produce somewhere so that the junction could be made between the 401 over and because the other part of our conviction tonight was that the Elliott Brothers computing effort was doomed. We didn't believe that it would survive. And we were wrong. We had a great loss. My opinions of that loss was that, in fact, the only people that we could touch who seemed to have a vision of what was going to happen, what might come. Nobody who was dealing with any of the other firms had that vision. And in the case of Brandy, there was the having attitude, which seemed to put limits on possibilities there of venturesome movement forward. I think we could appreciate this, and I think that our own resources, or perhaps by stimulating some spending part of the government, be more realistic about it, you could have kept the effort together, Elliott Brothers. The result, the end result might have been very much more effective for the industry in the long term. You see, looking back on it now, the people and the attitude which existed for wood were much livelier and more advanced than any of the firms in my view at that time. And it was an organisation which was comparable or comparable with being, in effect, the ERA or the Economorphy of the UK. And if their effort amplified support, Lannigan's financial support, they would have been then right, perhaps a year or 2 years later, to have joined up with one of the punch card firms to produce what would have in fact been the next generation, for something perhaps more advanced than what we produced in granted as in granted. But it didn't happen. But it really called for substantial expenditure. And NRDC was not, at that time, engaged in what might not have been recoverable expenditure.
And that was from its terms of reference, wasn't it?
Yes.
Whether
We would, as things went on, we would take more action later on. But in those days, we were looking hardly all the time at what we would get back in the short term from this investment in producing potentially.
Yes, that's my slight criticism. Short terms.
Yes, it is.
I don't think that personally that's the problem. I think the problem is that everybody in the computing business underestimated totally what you need to sell in a commercial business machine market. Elliott's tried to go around this. They tried to tie up with British Tab. I don't think it was an NRDC job to do that, and it was purely the shortcoming of the other management which turned that down. And so, if you like, I could say as a last resort, because we haven't had a technical edge, have made the tie-up with NCR, but that was clearly not going to last. The only thing that would have made any sense was if, yes, the Powers and an Elliott, or was it British Tab at that time, I probably was, had got together and then designed a machine with the appropriate peripherals and the appropriate type of order code structure. And that just didn't happen. But I don't think it's an NRDC fault.
Maybe it's not an NRDC fault, but I think that our attitudes fermented it, because we were always pressing to have something produced very quickly to meet some little perceived or imaginary market.
Yes, but John, you could have done that. You could have done that. By the time our two colleagues over here were choosing what computer they were going to have, the 405 was actually there and existing. The deal with NCR was coming about already. The one thing that we didn't have, and I'm the one person who could say this, we didn't have a very user-friendly order code. I produced it. So I can say, if Christopher Strachey had been working with us, and we'd had the user-friendly order code, we had a machine with the non-trivial advantage of existence. Yeah. And we sold just about as many, when you get down to it, as were sold of the Pegasus anyway, and sooner. So if you had the order, now coming back to the other thing, Hugh talked about hero friends. John Coles was a hero friend of mine and very much is today. But I do believe that whatever the cause, he did what great men should do. He got out. I didn't know about the way he got out. But those here today know that there were tensions in the teams between them and Coles at the time. So that,
Sorry, what do you mean by in the team between them?
I mean the people in this room, had, in the lab, had tensions with Coles. So John going, I think, was probably a very good thing. Just the way it was going.
Oh yes, I agree.
And the NRDC had the foresight to see that it wasn't, I believe, all that much money that was required at that stage. Okay?
That's right.
There was a little assistance,
I
like
agree.
this administration. But by the time the 405 was really going, it had a much better machine than we managed to make it. And it's very nice to make.
Inspired diplomacy with that.
Yeah, I happen to think that in the long run, I'm afraid, the short television of this country would have won, and we would have gone down the pan just the same.
Yes, that echoes what Ian Merry said. Pegasus seems to me to be a paradigm of this country's failings to recognize and foster our weaknesses, and therefore can't exploit our real strengths. Do you have any more comment on your
I
contributions?
rather associate myself with the last speaker. I think that the short-termism of this country is paramount. In essence, we have a kind of negative feedback which always leads us to mediocrity. And although I left Ferranti in order not to work for the military, I've actually worked nearly half my life in defence. I discovered in the latter half of my life that the military set up mechanisms to prevent that negative feedback taking place. We have none of those mechanisms in the structure of British society at large, particularly engineering. What happens is that you get the conflict between a number of dichotomies, between projects on the one hand and techniques on the other, between individuals on the one hand and organisations on the other, between tasks on the one hand and roles on the other. And it is always the latter examples that win through roles, organisations, techniques, when what we should be emphasising is tasks, individuals, and projects. If you don't do that, you lose. And if you only have to look at what happens in the United States, the environment there actually fosters the making of brilliant, successful, very, very rich engineers. I remember the chap that you gave me as my first assistant, Bill, finished up as a dollar millionaire because he joined Max Podolsky in the United States. Howard Marchant. And when they sold out to Xerox Corporation, he and all the other people who worked with Max Podolsky became instant dollar millionaires. That is the difference. Yes.
I'd just like to say that as somebody who works in the computer industry now, it hasn't changed a bit. I have the same frustrations, and I wish I could bring some of my managers along here today to hear some of the comments that have been made. I'd like to teach them things too, based on your experience, but they don't seem to learn.
Thank you.
But I think the point about the Elliott problem, I think, and Curl's problem, is that the laboratory proposal, I think others have hinted at, was organised around a techniques basis. You know, you had this and that and the other. And the only way you could run a business like that is if the guy at the top understands the technical depth of the whole affair. Right? The technical depth. And that wasn't the case. And the reason why I stayed with the Elliott's was because I was offered by the Elliott management, the commander based in Tyler, at the time of Dr. Ross back in Aegis, a project-oriented business. A project-oriented business where I, if you like, yes, control the drawing office and the mechanics and the whatever, and the economics. And that's why I didn't go with Cole's venture. I don't think it was Cole's fault necessarily that the land was set up like that. But he could have changed it, and he didn't. That's sort of what I have against Cole's. I think that it was an organizational clash. Right. Horizontal against vertical. I think he was a vertically oriented man around techniques. And the Elliott's believed vertically went on, and it went bust, so I mean, nobody wins. But was project oriented. And that has its problems too. I can tell you, but nevertheless, it was an advantage at this time against what you and Harry had problems with.
Yes, can I add a bit to that? Just a moment. Thank you.
So don't forget that those laboratories were set up on a request from the advocate to end clothes.
Yes.
Because they wanted to continue the expertise, to develop the expertise. No, not their distribution, they have a wide spectrum. That was going fine, I thought, what the man could do, when they were to pull the carpet from under them.
Yes.
And so, financial position took agree with the angle on which Coles and Barry Smith. That's an issue that took
You're saying the advert was put in the right?
Yes, that's pulled that one, yes. Yes.
I know they did, yes. You're saying that was the cause of the trouble.
That caused a financial trouble, which then caused, I think, this is my information, caused a trouble between the new couple, the Baggett, the Rosses, and the Birdshells, and Cole on the line.
Yes.
That's right. Could you possibly ask people to state their names and affiliation?
Carry on, David.
Elliott, yes. I'd like to, first of all, agree 100% with what Andrew said there. But I do see a great difficulty at that time of setting up a project in a technology as new as this, where we had absolutely no infrastructure to help it. You had so many different technology required to make the new bits, and you couldn't possibly have an expert in each of those technologies in your project.
Right.
And keep him happy and busy.
Right.
So at that stage, the only way is to start with a technical, but you have to take special steps to make certain that the project is properly organized within that, so that there aren't these conflicts of watertight doors between them.
Yes. Yes.
And I think that was the trouble.
I'd like to ask John Crawley, was it not the fact that there were these many techniques that you saw which attracted you to it?
Yes, that was one of the fact that we were it's quite clear that the instructional techniques were going to advance. We never realised what they would become. So the work of Elliott Brothers showed some substantial use for instructional techniques and sounds. They were sort of somewhere. Now, is there anyone there who can say what sort of mistake IBM got to in their research efforts in say 53 or my impression is that by then they had research activities going on, practically all the possible forefronts of technique.
I think so, yes.
In fact, they were able to afford to do that.
Perhaps somebody can confirm this. Sorry, I heard about IBM. 6 billion was made quietly in a garage, being carefully kept out of the knowledge of the top management. Otherwise, it would never have been made.
Have you taken to that garage at the bottom of the field and have been shown the PowerPoint that it was plugged in?
Thank you for confirming that.
But now they can stop it from being a rather mediocre machine.
Right.
Right, yes, it's true.
Colin Murphy, formerly NRDC, Ferranti, and ICL. The impression I got at one stage was that the British government thought the worst thing they could possibly do was to give unfair preference to one of their manufacturers. And that at one time they were handing out fair shares of contracts to 13 different computer manufacturers in this country, whereas the Americans wanted to get their North American defense shield working, and they favoured one manufacturer. And that gave IBM a insuperable advantage. And now the EC were behaving the same way again.
When you say place of contact with 13 firms, that was under ACTP.
I don't know what it's for. I had a dream once of a cartoon, and the cartoon had 13 boxers in a ring with a referee named Mintek, or DPI, whatever they were then. And there was an IBM man and a deck man sitting outside the ring. And in cartoon number 1, one of the people was down on the ground, and the reps were saying, "John, money, money, money," pouring it in. And the next one, another one was on the ground, and the next one, another one was on the ground, and the last one, they were all on the ground. And the IBM man, the jet man, Having said that, can I just say one ray of hope, though? It is gloomy, but I don't think one should forget that GEC Avionics, which is essentially the Elliott organisation from Boreham Wood, is now probably the leading avionics firm in the world.
I'd just like to make one brief point about this punch card business. I never agreed with Forsbury when he contended that the computer business should be run by one of the punch card people or two together. I reckon that we wanted punch cards to be able to feed into them. And of course they were an invariable, enormous storm. But the real secret of computers, as Bowden and I discussed it, always was the quick access, particularly for the scientific kind of work. We also were influenced by the fact that Horace cards were suitable for scientific work, but Howard cards were not. They were useful for things like insurance companies, where you never wanted to alter the program unless you had to. But for scientific purposes, such as I was concerned with in ICI, Horace had enormous advantages, obviously. So it came to a point where I was asked to negotiate with both these punch card people about import. I won't go into details of why this fell down, but the politics, internal, external. But the answer was that, I say, sadly, it's the only point at which Holmesby and I think have disagreed, I think, but I have great admiration for his foresight. That's Bellrost and NCR at that time. At that stage, obviously, it was too early to be application for computer people to concentrate on the various applications. But I fear that what happened in Britain is that the computer was a new scientific gadgets, toy, very clever toy, which was developed by scientists. And I don't think they were sufficiently customer friendly, if I may put it like this. They didn't look at it from the point of view of how the customer would find it, how easy it would be to use the computer, both from the programming point of view, from the reliability point of view, and so on. It worked beautifully in the laboratory, but not necessarily on site. Lawrence Clark mentioned some of the things about the order code, which is also one of the aspects. I was involved with making the first 405 work, and I had the same problem with Mr. Merrick, probably much worse ones. The wires were all half broken. It took about 18 months to make the first computer work before I got onto it. And what we did, we had to strip all the wiring, strip everything, start afresh, because the wiring was bad. We had to, apart from all the dry joints, we had to rewire the whole thing, we had to look at contacts, do a lot of offline work, and then I remember we had an argument between Elliott and ourselves. But Elliott said, don't touch the computer, because if you do too much to it, it's bound to go wrong. And I said, no, if that is so, be as violent with it as possible to make sure that all these intermittent faults and all these weaknesses are taken out of it, so that when the customer gets it, we can really handle it roughly. And that was, I think, an important aspect. And the same applies to looking at it from the customer's point of view, rather than from the scientist's point of view. And that is perhaps also why the Americans tend to be more successful, because they tend, from the business point of view, to look at things from the customer's point of view, rather than just the scientific invention.
Yes, it was standard practice on the Atlas II that became mathematical. They were under the hammer.
Well, that was in the beginning. We didn't do that afterwards, because when we finished with it, it was
Bit of wood on it.
really live.
I'd like you to add 2 points to the last speaker's remarks about user-friendliness. I remember my enormous disappointment when I went to a computer conference in 1964 in Edinburgh, which was largely advertised as, I can't remember the exact title, it was the computer user.
Yeah.
And every single paper, as I recall, was about the programming. Well, that's the first. By 1964, there were many computer users who were using, for instance, airline reservation systems, who had nothing to do with programming. The computer using was entirely different. But that was a point of view that never got across in this country until about 1980. Secondly, as far as programming is concerned, in the United States, it got an enormous advantage from the very effective, if rather dismal, activities of Grace Hopper. The pushing of COBOL, the invention of COBOL, and the pushing of COBOL totally transformed the business world in the United States. It still has. COBOL may be the most dreadful language in the world, but it is nevertheless the single largest reason why the United States has made such enormous advances in business computing.
Do Ross.
Elliott and Brandy, and ICL and STC. I've had the advantage of reading Mr. Wilkes and Mr. Gearing's papers beforehand and do a little thinking about it. And the point I want to raise relates to this much praised NRDC idea that computer firms and punch card firms might get together. Both Mr. Wilkes and Mr. Gearing revealed that they had to work for 6 years within their organizations before an order for a computer could be placed. Now, this is reflecting, it's a vivid piece of evidence as to what was actually happening in those days. It was phenomenally difficult for the companies who had potential, what we now realize are commercial data processing tasks. It was terribly difficult for them to realize that these could be put on a computer. Likewise, it was very difficult for us in the industry to see how computers could be developed in order to meet this potential need. And so it was inevitably a fairly slow process of making technological advances one by one, which would make these commercial data processing activities possible. The first one, undoubtedly, was when we got magnetic tape, which could be relied upon over a period of years to be error-free. That wasn't much to do with the tape itself, but to do with the logic and the programming for using the tape, which, in my experience, was developed by my colleagues in Manchester first. Then we thought it would be desirable to be able to get data into the machine from punch cards. We thought it would be quicker to do that. But this was not real data processing in the sense we use it. So the whole of this time was a period of exploration. Exploration of technology, exploration of new techniques, exploration of what the users wanted, exploration by the users of what they could do. And it's not really a surprise to me that it took the time it did until we got practical data processing systems. And I'm sure that any idea that this could have been done in a flash of a hand, by government money, by some ministry doing this and that, is just pure pipe dream. It had to be done by good, hard work, with lots and lots of people getting stuck into the job.
Two more questions.
Yes, rather sure. Thanks to Susan for days. To some extent, what I'm going to ask has been anticipated, but not completely. From my personal knowledge of Pegasus, and I dare say this is true of the 405 as well, but actually either machine was sufficient for technically for the task in mind. As I dare say as the IBM 650, for example, not better. So could it have been that the problem was that not enough people bought them, perhaps because they weren't well enough marketed?
Could I make a point there, Chairman? On that marketing. When I was in the States in '54, I talked with the Vice President of one of the big machine companies who happened to be an Englishman. And he asked me what British manufacturers were doing about computers. I told him what I knew then, that in fact people like Elliott, Brandy were doing things and promising things, but that the two card companies, British Tablet Machine Company and Power Centre, hadn't any general purpose computers at that time to offer. And it seemed to me at the time that British Tablet Machine Company were almost likely to go under to IBM competition, as IBM had come into this country as the exclusion arrangements no longer applied. And he said something that's always stuck in my mind. He said, I can't see the whole of people surviving long. In this business, you need a worldwide market and good marketeers. It doesn't matter how good your equipment is, if you haven't got a huge market, which means a worldwide market, you will not get the finance to pay for development. Now, I think that was a very deceptive comment on the computer business.
I think that would be true if it didn't have an example to the contrary. In fact, two examples to the contrary. Japanese have made themselves both incredibly effective in the automobile industry when they didn't even have a national market. And they have now made themselves very, very effective in the computer business when they have no marketing working alike.
I think what's interesting about that, certainly in the North field, is that somebody said to me that they have earned a reputation for producing reliable machines, and the British haven't.
Nothing beats a good product.
Right.
Well, very further point, or maybe a minor one. I do agree with you with Ross. I think it's hard work to get together because it's computing. Computing is always difficult. It's not. It was a new world for everybody. I do, however, think there was a lot to be said on a lower scale that it portrays the business if the punch card side, which was well established as a handling machine, data, right? Well established, gone ahead, whereas Elliott and I think Barati and others came in from a paper tape angle because the punch card people were frightened to let us use that word. I was fascinated to hear, which I didn't know before, that you put a bull machine line printer on a Pegasus. We put a bull printer on a 403 for exactly the same reason. It wasn't that you couldn't get together, is that they represented you. And I do think that if they're going to get together at that stage on the computer techniques which were working in these companies and the practical usage, which both of us, I think certainly Cyril has, of punch cards. They wanted to go on from punch cards, right? And I think that the fact that we had to develop a card reader in Elliott, which was never much good, and we shouldn't have had to do it. We should have been able to attach it to somebody else. But they wouldn't play. They wouldn't play at all.
That possibility answer the problem. The answer to this is that they were established in the wrong, in some cases, the wrong principle. I'll give you a simple little example. When we were establishing the army punch card system, there was one incident being used also as an index for the army created and was being used for recruitment purposes, obviously. Now, there was an incident down at Cheltenham when there was an excellent IBM, British madman in charge of the one there. And Nigel Borchin, among others, was concerned with the use of this data for personnel selection. And there was an occasion when Nigel pointed out that the right way to use these scholars, having gone for one particular purpose, which was to recruit a certain number of men for a particular farm. Having done an initial sort, as soon as you've got enough people who would be suitable for that arm, you cut the rest, you see, and use it. Of course, they don't analyse as much as you need to, generally speaking, nothing at all. And so the man in charge of the machine, as Nigel refers to as the man in charge of the Iron Horse, couldn't stand this because he'd been brought up on the principle that you work through a program and then you came to the conclusion. Well, now we're talking about man-machine interface.
Could I make a quick point that Pilot Ace and NPL and the English use punch card machines essentially, for example. This was fortuitous because NPL were great users of punch cards for academic calculations. And it was advantageous in various situations, particularly business situations. There is an indication that other computer manufacturers could have switched to establish punch card machinery from suppliers if they thought of doing so. We can claim no credit because we did it for fortuitous reasons.
Last question.
It's not so much a question really, it's a comment, General, on the day's proceedings. I think I'm unlucky really. I seem to have been born a couple of generations too late actually. I have great admiration for many of the people in this room when you consider today the latest sort of microprocessor has got God knows how many million transistors on a chip, to actually be able to build a machine capable of doing the type of calculations and programming with the small number of active elements. I mean, I think a quick calculation shows the 803 had about 2,000 gates in it. Now, if you were to go to a modern designer and say, build me a computer capable of solving this problem, but you've only got 2,000 gates to do it with, they'd tell you to go packing.
Nicholas had 80 gates.
There you are. Yeah? You guys, you were streets ahead of anything around today. Today they just double the number of chips on the number of transistors on the chip and carry on adding more and more power. I mean, they just didn't. They've got no idea how to design logic, in my opinion. Like they have
on that happy note, we'll draw the seminar to a conclusion. I would like you all to show your thanks to all the speakers who've spent so much time and energy putting all this together. But before you do that, I would invite you all to come across to the old canteen building where we've laid on some drinks and sandwiches and where you can actually